Right. Okay, good morning. It is a great pleasure to introduce Richard Stanley from MIT. Richard has been a leader in combinatorics during the last 30 years, and he found many deep, profound, and fruitful links between combinatorics and other areas of mathematics. Much of his work has to do in one way or another with enumeration, perhaps the most ancient area of combinatorics, but at the hands of Richard, the study of enumeration problems is always blended with algebra and geometry. Richard has been able to develop and apply deep techniques from commutative algebra in discrete mathematics. His breakthrough proof of the upper bound conjecture for spheres led to an attractive theory of Cohen-Macaulay complexes at the intersection of combinatorics and commutative algebra. Richard is a member of the US National Academy of Sciences and received many awards, including the Polya Prize, the Steele Prize, and the Schock Prize. He has supervised 46 PhD students. That's really remarkable, and I'm sure this number will keep growing, maybe even during this lecture. His students include many of the very best young researchers in algebraic combinatorics in the world. I first met Richard more than 20 years ago, and I know that besides being an outstanding mathematician, he is a superb speaker as well, as I'm sure we'll all see today. The title of his lecture is Increasing and Decreasing Subsequences. Richard Stanley.
Okay, thank you, Noga. Maybe that's a little small. It's better. Okay, so I will start out by defining what I mean by increasing and decreasing subsequences. Let's suppose we have a permutation of the numbers from 1 to n, and I illustrate it here for n equals 9. I write my permutations as just a sequence of the numbers from 1 to n. And an increasing subsequence, shown here on the top in red, is a subsequence of elements that appears in increasing order. 3, 4, 6, 7. And similarly, 8, 4, 2 would be a decreasing subsequence. And what I'll be mainly interested in this talk is the length of the longest increasing subsequence, the number of terms. Now, here, this red sequence is one of the longest, and the longest one has length 4, and this is one of them. So ISW will denote the length of the longest increasing subsequence. And similarly, DSW is the length of the longest decreasing subsequence, which is 3. Well, before I begin the mathematics, I should point out that there are real-world applications of increasing subsequences. And I will mention this application to airplane boarding, which was also discussed yesterday by Percy Deift in his plenary talk. So we'll make this very naive model first for passengers boarding a plane. We have, say, 6 seats, and we have our 6 passengers, and they just come in random order, and they have these assigned seats. And the algorithm they will follow is that they just we'll just assume that they take one time unit to be seated after they arrive at their seats. So at first, 2 will go to his seat. There's no obstructions, and 1 to his seat. But 5, 3, 6 have to wait behind 2, and 4 behind 1 before they can move on. So 2 and 1 sit down, and then the remaining passengers will continue. You can see a kind of a defect already in this model, unless you assume the passengers are very thin. But 1 and 2 have sit down, and now 3, 6, 4, and 5 move as far forward as possible. Then 3 and 5 sit down, and then in the last step, 4 and 6 sit down. Well, it's very easy to see that the total waiting time here, the number of steps in this algorithm, is the length of the longest increasing subsequence of W. Well, as I said, this is a very simple model, but Bachmat and his collaborators have come up with much more sophisticated models in which increasing subsequences and a lot of the theory I will discuss play an important role. And 2 of their main conclusions were the following: that the usual system that airlines use for boarding, which is back to front, is really not much better than random in the amount of time it takes to board. A better system is to first do the window seats, then the center seats, and then the aisle seats. And I think some airlines have actually moved to this system. Okay, so now we'll start in with some of the mathematics of decreasing subsequences. Now, one aspect of this subject that makes it so interesting is that these subsequences are connected unexpectedly with many other topics. And the first one I want to talk about is Young tableau. So I'll start out with a definition of a partition of an integer n, denoted this way. That would be a weakly decreasing subsequence of non-negative integers that sum to n. And we can represent this partition by this Young diagram of squares. There are lambda I squares in the ith row, and they're left justified. So this is the diagram of 4, 4, 3, 1. And they'll also be needing the concept of the conjugate partition, the one you get from the diagram of lambda by transposing the diagram, or changing rows to columns. So the conjugate of 4, 4, 3, 1 is 4, 3, 3, 2. Now, a standard Young tableau, or SYT, of shape lambda, some partition of n, illustrated it here, which should make the definition clear. You insert the numbers from 1 to n into the squares of the diagram so that every row and column is increasing. So F lambda will denote the number of standard Young tableau of shape lambda. So, for instance, for the shape 3, 2, there are 5 standard Young tableau. So F 3, 2 is 5. Now, it's quite surprising that there is actually a very simple explicit formula for this number F lambda, the famous Frame-Robinson-Thrall hook length formula. I won't bother to state it here, but when these F lambdas come up in later formulas, you should realize that they can be replaced by this very simple explicit formula. Now, I'll just make a note that this subject of increasing and decreasing sequences has a lot of connections with representation theory. I don't have time to go into any details, but it can be seen by the fact that F lambda, which I will soon be tying in with increasing subsequences, these numbers F lambda are the dimensions of the irreducible representations of the symmetric group. But I won't be saying anything more about this. Now we have to connect permutations with standard Young tableau, and the way this is done is by this famous Rsk algorithm, which gives a bijection from permutations of 1 up to n in pairs of standard Young tableau of the same shape, which is some partition lambda of n. So I take my permutation and I have to produce these two standard Young tableau from it. I will call this, whatever the shape lambda is of these two standard Young tableau, the shape of the permutation W. I should explain where the letters R, S, K come from. R is Gilbert de Beauregard Robinson, who first defined this in a vague form. Craig Shenstead, who later changed his name to Ia. He made it much more explicit and also proved this key connection with increasing subsequences. And K is Donald Knuth, who developed this theory further. Now I'm going to describe this Rsk algorithm with an example. This is not quite the standard way of describing the algorithm, but it's most convenient what I'm going to do for purposes of generalization in a little while. So what I do, say my permutation is 4, 1, 3, 2. I put 2n dots in a row like this. So here n is 4. I write my permutation under the first n dots, 4, 1, 3, 2. And then the next n dots are just the numbers from 1 to n in decreasing order. I draw an arc from two vertices with the same number. And so I have this matching of these two n vertices. And now what I do is I go across, I scan these numbers from left to right. When I encounter a number for the first time, which will be this, the way this is set up, the first half here, I insert it into a tableau. And when I encounter it for the second time, I delete it. Now, I won't define the details of this insertion process, which is the key step in the Rsk algorithm, but there is some simple rule for how you insert a number into a tableau, keeping the rows and columns increasing. So I first insert 4, then I insert 1, and I'm going to get this. Then I insert 3, I will get this, and then when I insert 2, according to the insertion rule, I'll get this tableau. Then I delete 4, I delete 3, I delete 2, and I delete 1. So I'm back at the empty set. And I read off my pair of standard Young tableau, PQ, as follows. Right in the middle, we're going to have a standard Young tableau with n squares, and that will be P. 1, 2, 3, 4. For Q, I look at the order in which this middle tableau has been built up. I first added an entry here in this square here, so I put a 1. The second square that I added an entry, this 4 here, I put a 2. Then here, the third square, I put this 3, so I put a 3. So this second tableau records the order in which the entries have been built up. And in this way, I get a pair of standard Young tableau associated with this permutation. And it's not hard to see that this is a bijection. Given any pair of standard Young tableau of the same shape, I can uniquely recover this permutation. This is one of the fundamental algorithms of algebraic combinatorics, and I could argue if I had a couple of more hours, one of the most interesting of all mathematical algorithms. What does this have to do with increasing and decreasing subsequences? Well, the theorem of Shenstead is that if a permutation W corresponds to this pair PQ, or the shape of P and Q or partition lambda, then the length of the longest increasing subsequence of W is just the longest row length of lambda, that is the length of the first row, and the length of the longest decreasing subsequence is the length of the first column. So this was the example from the previous slide. 4, 1, 3, 2 went to this pair. The length of the first row is 2 elements in the first row. So the length of the longest increasing subsequence is 2. Now, it's not so easy to actually recover from these tableaux an increasing subsequence of length 2. But so it's not such a simple, it's not just that this first row is necessarily such an increasing subsequence. I mean, it isn't a simple example, but it's more subtle than that. And similarly, the length of the first column is 3, so the longest decreasing subsequence of W has length 3. Well, one immediate corollary to this bijection and Schoenstedt's theorem is the first theorem ever proved about increasing and decreasing subsequences, this famous Zakoris theorem, one of the first theorems of extremal combinatorics. Suppose W is a permutation of PQ plus 1. Then either there is an increasing subsequence of length greater than P or a decreasing subsequence of length greater than Q. Well, if you think about what's going to happen when you apply Rsk to lambda, if the contrary were true here, the longest increasing subsequence had length less than or equal to P, and dsW was less than or equal to Q. By Schoenstedt's theorem, lambda 1, the first row, would be have at most P squares. The first column would have at most Q squares. So the whole shape would fit in a P by Q rectangle. It could have at most P times Q squares. So that would be the number of terms in the permutation. So that's the proof. Very simple from Rsk. And we also can say something about the extremal situation when we do have an increasing subsequence. Let's say, without loss of generality, P is less than or equal to Q. If we look at the number of permutations in SPQ, whose longest increasing subsequence has length P and decreasing subsequence has length Q, so if this were PQ plus 1, there wouldn't be any by the Zakoris theorem. This theorem is best possible in that there do exist such W, and we can write down the exact number, because the only shape with PQ squares, first row of length P and first column of length Q, is a P by Q square. So Rsk will give this pair of standard Young tableau of this rectangular shape P by times Q. The number of pairs of such standard Young tableau is just F lambda squared, where lambda is that shape. The hook length formula will give this, as I said, gives an explicit formula for this number, and when you apply it to this situation, you get this very mysterious looking formula, if you didn't know this theory, for the number of these permutations, these extremal permutations. In fact, I don't know a simple reason why it's a perfect square without going through this Rsk. Well, as a kind of aside, I'll mention a kind of cute result of Dan Romick on what a permutation looks like typically that lies in this set that has ISW as P, DSW as Q. And it's a permutation of 1 up to PQ. So I'll just state this sort of intuitively. If you take your permutation W and look at the permutation matrix of W, which we think of as lying in the coordinate plane with vertices coordinates plus or minus 1. And then we look at the location of the 1s in this permutation matrix. So here's an example for P equals 4. So we have a permutation of 16 elements. Longest increasing subsequence is 4, and longest decreasing subsequence is 4. I've filled in these squares where the 1s appear. But even this small example, it looks like it might be filling out some curve. Well, it's much too small to see what's really going on, but Romick showed that indeed this is the case, and this curve is this 4th degree polynomial curve. And this is its graph. So this is a kind of amusing theorem about the typical extremal permutations when P equals Q. Well, what can we do next? We can ask for the distribution of the length of the longest increasing subsequence. A very interesting problem. So the simplest question is, what is its expectation? So I'll let En be the expectation of the length of the longest increasing subsequence. That is, and this is with respect to the uniform distribution on the symmetric group. So by the Rsk algorithm, if we applied Rsk to our permutation W, we'll get a certain shape lambda. The number of pairs of standard Young tableau of that shape is f lambda squared, and the lambda 1 would be that's the length of the first row, would be the length of the longest increasing subsequence of W. And so the expectation of the length of the longest increasing subsequence would just be this sum. Now, Ulam was the first person to ask about this question. What can we say about the distribution of ISW in general, and in particular about the rate of growth of the expectation? The first significant progress was made by Hammersley using sub-additive ergodic theory. He showed in 1972 that the rate of growth is a constant times the square root of n. That the limit as n goes to infinity of En over the square root of n exists. It's some finite constant which he proved was between pi over 2 and E. And he conjectured that it was 2, and numerical evidence obtained by Ulam and collaborators supported this conjecture. Well, this was actually proved. This constant is indeed 2 independently in 1977 by Logan and Shep and by Vershik and Karol. Well, actually, Logan and Shep only proved the more difficult inequality that C is greater than or equal to 2. Vershik and Karol found a clever argument using Rsk that is less than or equal to 2. But the idea of the proof is to use this expression in terms of f lambda, the number of standard Young tableau of shape lambda. The number of terms in this sum is very small compared to the size of the sum. The number of partitions of n is small. This is bigger than n factorial, which is much bigger than the number of partitions of n. So E of n is going to approximately be just 1 over n factorial times the largest term. I'm not being very precise here, but this suggests that we want to find the lambda for which f lambda is maximized and figure out what its longest part is, its largest part. You can take this discrete maximization problem here, and by using the hook length formula, and when n goes to infinity, you'll get a continuous problem in the calculus of variations. What we want to do is find this curve where we normalize the area under the curve to be 1 so that we minimize the logarithm of, we're integrating over under the curve at every point, this distance plus this distance. So this is what the problem reduced to, and this was what was solved by Logan, Shep, Vershik, Karol. It's not so easy to guess this curve. This is what it turned out to be. I think you need pretty good eyesight to see that this is its equation. It's given parametrically by these equations. X is y plus 2 cosine theta, and y is 2 over pi sine theta minus theta cosine theta for theta between 0 and pi. The fact that it hits the x and y axes at 2 immediately proves that this constant C is greater than or equal to 2. And I mentioned that Vershik and Karol found this very nice proof using Rsk, just a very elementary argument that it's less than or equal to 2. Okay, so that's now the problem of the expectation, and the next step is to try to get even better information about the actual distribution of the length of the longest increasing subsequence. Well, to do that, you need some kind of formula for the distribution in the discrete case. And so we'll let uk of n be the number of permutations such that the longest increasing subsequence of W has length less than or equal to k. And I put a sub n here because I'm going to be letting n go to infinity. So let's put this n in here to be clear. So we need some kind of expression for this in order to deal with it analytically and try to see what happens as n goes to infinity. Now, the first such result, again due to Hammersley in 72, was that U2 of n, the number of permutations with no increasing subsequence of length 3, is a Catalan number. So this is one of the many combinatorial interpretations of Catalan numbers. Many of you know that I have been collecting these interpretations, and actually now I have over 140 of them at this web page. Well, for higher values of k, it's not so simple. But Ira Gessel was the first to prove in 1990 a generating function for these numbers for fixed k. So we'll look at this generating function, sum of uk of n, x to the 2n, and it turns out you need an n factorial squared in the denominator to give a result. And it turns out to be this k by k determinant of certain kinds of Bessel functions. It doesn't look so promising at first. It looks like a pretty complicated formula to actually extract good asymptotic information from. So, for instance, when k equals 2, we'll get this 2 by 2 determinant. This is what the determinant is equal to when you expand it out. And it's easy to see that indeed this is a generating function for Catalan numbers, recovering this result of Hammersley. Now, an interesting result, the corollary to Gessel's formula, is that although there's no simple formula for uk of n in general for arbitrary k, it can be computed quickly. It's what's known as a p-recursive function for fixed k. It satisfies a linear recurrence with polynomial coefficients. And here is what U4 and U5 look like, what the recurrence looks like. So, of course, once you have figured out what these recurrences are, there's very quick polynomial time to compute the values of these functions. There are some interesting conjectures about the exact form of these recurrences due to Bergeron, Favreau, and Kroll. Okay, so now that we have a formula of sorts for these numbers uk of n, we can try to understand what happens as n goes to infinity. And this is this pioneering work of Bake, Deift, and Johansson. They found the limiting distribution, properly scaled, of the length of the longest increasing subsequence. This was also discussed yesterday by Percy Deift. And this was defined, well, to define this distribution, we need the so-called Painlevé 2 function. We look at this nonlinear differential equation, the Painlevé 2 equation, and it belongs to a certain class of differential equations that were classified by Painlevé, and with certain initial conditions that essentially it's asymptotic to what happens if this standard solution if you get rid of this nonlinear term, the Airy function. So I will need this function to define this Tracy-Whittem distribution. Before I do that, I think I'll digress and say a little bit about this mathematician, Paul Painlevé, because he had a very interesting life. He was born in Paris in 1863, and he was an excellent mathematician, as shown by him winning this Grand Prix des Sciences Mathématiques in 1890. In 1908, he was the first person in history to be a passenger in an airplane, and he set a flight duration record of 70 minutes. For 2 years, he held a position equivalent to being Prime Minister of France. So, and to end the story, he died in 1933. Well, going back now to the mathematics, we'll define in terms of this panel of A function U of x, this probability distribution, the Tracy-Widom distribution, f of t is this, well, it's just completely pulled out of the air if you haven't seen it before. Why would anybody think of such a probability distribution? But it turned out this is exactly the distribution that describes the limiting behavior of the length of the longest increasing subsequence. What we have to do is scale it properly. We subtract the mean, which is asymptotic to twice the square root of n, divide by the standard deviation, which turns out to have order n to the 1/6, and the probability that this quantity is less than or equal to any real number t as n goes to infinity is f of t, the Tracy-Widom distribution. So this was a spectacular breakthrough in this subject. And various nice corollaries can be drawn about the distribution of increasing subsequences. In particular, the length of the longest increase. Actually, this should be the expectation here of the length. The EM, the expected length of the longest increasing subsequence. Remember, it was asymptotic to twice the square root of n, and this result gives you the second term, a constant times n to the 1/6. And that constant is defined in terms of the Tracy-Widom distribution. It's about minus 1.7711. So how do you prove this theorem? Well, Gessel did all the combinatorics, so as far as I'm concerned, after that it's just analysis. But of course, that's 99% of the proof, and I'm not going to go into any details there. But we could ask, since this Tracy-Widom distribution, which I've written here, and with this panel of 8 function again written here, that had already been defined when Bake, Dijkstra, and Johansen proved their result. So where did this come from in the first place? This is going to give one of these unexpected connections of increasing subsequences and other topics, this time random matrices. So, again, Percy Dijkstra defined this yesterday, the Gaussian Unitary Ensemble, a certain probability distribution on Hermitian matrices, n by n Hermitian matrices. Anyways, it's defined this way. It's not so significant here, the exact definition, but this is some very standard natural probability distribution on these matrices. And Tracy and Widom showed that the largest eigenvalue of a random Hermitian matrix chosen from this GUE model is properly scaled or normalized in this way. Also, satisfies the Tracy-Widom distribution. So here we have it seems like two completely different ways in which this distribution has arisen. And in terms of increasing subsequences, their distribution, and eigenvalues, the largest eigenvalue of a Hermitian matrix. We could ask, is this connection just a coincidence, or is there some connection? And the connection was actually given by Andrei Okunkov, who a couple of days ago won a Fields Medal here. And I'll just say a couple of sentences about what he did. Namely, you look at the theory of random topologies on surfaces. And the reason that there are these two interpretations or two places where the Tracy-Widom distribution appears has to do with the fact that there are two ways that a surface can be described. We can glue polygons along their edges and build up the surface in that way. And this way, well, in this theory of quantum gravity that physicists have developed, this way of building up surfaces has been shown to be connected with random matrices. We can also think of a surface as a ramified covering of a sphere, and then the combinatorics of permutations comes into the description of the surface. So, extremely brief indication of why these two subjects are related. Okay, so I think that finishes the highlights of the subject of increasing and decreasing subsequences of permutations. Now we can think about generalizations and analogs, refinements. Many of these are discussed in my paper for this conference. I will just pick out one here, which is a joint work with these four Chinese co-authors, Bill Chen, Eva Deng, Rosina Du, and Catherine Yan. And this is when we will replace permutations with another combinatorial object, matchings. So a complete matching, we'll have two endpoints, and we'll join them by n arcs, no two arcs with a common vertex. So here is a complete matching. If you want, it's a way of dividing these two endpoints into n blocks of two each. And our two properties of matchings that we're going to be interested in are really the pairs of edges of the matching are crossings like this. Two edges cross in their interiors. And nestings when one edge is contained inside another. Now the total number of matchings on the bracket 2n, which means the numbers from 1 up to 2n, it's easy to see that it's this 2n minus 1 semifactorial, the product of all the odd numbers from 1 to 2n minus 1. And in fact, we have another interpretation of Catalan numbers as a number of matchings on these two endpoints with no crossings, and also the number of matchings with no nestings. It's surprising we get the same answer both times. I will give a sketch of the proof of this theorem by giving a bijection between these matchings that we want to count, those with no crossings and those with no nestings, and something that's well known to be counted by Catalan numbers, namely so-called ballot sequences, sequences of 2n ones and minus ones, where every partial sum is non-negative and the total sum is 0. So there's n ones and n minus ones, and we put them in order so that all partial sums are non-negative. Well, the bijection between matchings with no crossings and these ballot sequences is very simple. Here's our matching without any crossings. We just label every left-hand endpoint of an arc by 1 and every right-hand endpoint by minus 1. It's very easy to see that this gives a bijection. This sequence here is a ballot sequence, and it gives a bijection between these matchings and ballot sequences. It's kind of surprising. Exactly the same rule works for matchings with no nestings. The left-hand endpoints get labeled by 1 and the right-hand endpoints by minus 1, and it still gives a bijection with ballot sequences. You have to think about that for a few minutes at least, I think, to see why that's true. But anyway, this is why we get Catalan numbers. Now what we would like to do is we'll develop a theory for matchings analogous to increasing and decreasing subsequences of permutations. So what should be the correct analog? Well, a first attempt would be that we can think of a matching in a very obvious way as a fixed point free involution. So actually, it's a kind of permutation. We just label the vertices 1 to n, and if two numbers are being matched, they are transposed by a fixed point free involution. So we just get this permutation Wm associated with our matching, which has n cycles of length 2. And we could say, well, let's just define the increasing and decreasing subsequence of a matching to be the, correspond to increasing and decreasing subsequences of this permutation. Well, the flaw in this definition is that there's no longer any symmetry between the two statistics. For permutations, it's obvious that increasing subsequences and decreasing subsequences have the same distribution because you can just reverse the permutation. But actually, if you restrict the permutations to be fixed point free involutions, these distributions are actually different. So we need something else, and this is what turns out to work: the most number of mutually crossing edges and the most number of mutually nesting edges. So if M is our matching, CR of M, the crossing number of M, will be the largest K, so that there's a K crossing, so that there exists K edges, any two of which cross. And similarly, the nesting number of the matching, NE of M, will be the largest K such that any two of them nest. So we get this picture. Now actually it turns out that this nesting number is 1/2 of the length of the longest decreasing subsequence of this permutation here. So that we associate with the matching. So actually the decreasing subsequence is a good analog, but we need, instead of increasing subsequence, we replaced it with crossings. Though it's certainly not clear that these have the same distribution. Unlike permutations where increasing and decreasing subsequences obviously have the same distribution. But in fact, this is the case. In fact, not only do they have the same distribution, but they have a symmetric joint distribution. If we let f sub n of ij be the number of matchings on two endpoints with crossing number I and nesting number j, then Fn of ij is Fn of ji. So in particular, the number of matchings with a given crossing number k equals the number of nestings, equals the number of matchings with a given nesting number k. So the case k equals 0 when there were no crossings and no nestings, I did previously shown that they were both equal to the Catalan number, and here we have this generalization. But unlike the case for permutations where increasing and decreasing subsequences, as I said, obviously have the same distribution, I don't know a simple reason why this is true. That's an interesting problem, to find a simple sort of bijection on matching that transforms the crossing number into the nesting number. What we have to do here is go through an Rsk type argument and find an analog of Shensted's theorem. So the main tool now is going to be a generalization of standard Young tableau, which I'll call oscillating tableau. We can think of a standard Young tableau as a way of building up a diagram of a partition one square at a time. The square in the standard Young tableau in which the 1 goes is the first square. Then we add another square where the 2 goes. Then another square where the 3 goes. Well, for oscillating tableau, you can add or remove a square at each step. So here we have an oscillating tableau. We always will start out at the empty shape. Here in 8 steps, I've ended up at this shape 3-1. So this has shape 3-1 and length 8. At every step, I've either added a square or taken away a square, always maintaining the diagram of a partition. There's no really simple way to represent this as one kind of tableau, like for standard Young tableau. You need this whole sequence. Well, now, how do oscillating tableau come into the theory of matchings? here is our matching, an example of a matching. And I'm going to do something almost completely analogously to what I did with the Rsk algorithm, in which we encoded a permutation by a special kind of matching. Those matchings whose right-hand endpoints are all at the end. We label the right-hand endpoints of these arcs from 1 to n, from right to left. 1, 2, 3, 4. The right-hand endpoints are in decreasing order from left to right. The left-hand endpoints get the same label as the right-hand endpoints. And then we're going to do the same procedure that we did for Rsk. We're going to scan this sequence of numbers from left to right. Every time we see a number for the first time, that is the left hand of an arc, we insert it by the Rsk insertion rule, and when we see it for the second time, we delete it. So I insert 4, I insert 2, no, I delete 4, insert 3, insert 1, delete 3, delete 2, delete 1. So we're going to get a certain sequence of tableau. And we only want to remember their shapes. That will be an oscillating tableau, because at each step we've either added one square or removed one square. It's an oscillating tableau with 2 end steps, and it's of empty shape. It starts out with the empty shape, and it ends up with the empty shape. That will be the oscillating tableau corresponding to this matching. And it's not hard to see, although it's a little bit tricky, because I'm only remembering the shapes, not the numbers inside of these shapes here. But it turns out, just from this knowledge of these shapes, you can recover all of these numbers in the entire matching. This map, phi, from matchings to oscillating tableau, is a bijection from all the matchings on 2 endpoints to the oscillating tableau of length 2n and empty shape. Well, again, I'll say a quick word about representation theory. Comes into this picture in the same way that it came into the permutation picture. The number of oscillating tableau of length 2n and empty shape, well, then it would be the number of matchings on 1 up to 2n. This 2n minus 1 double factorial, that is the dimension of the Brouwer algebra, the centralizer algebra of the orthogonal or symplectic groups operating on nth tensor power of the defining representation. Anyway, this is a well-known algebra in representation theory, and it plays the role for oscillating tableau that the symmetric group plays for standard tableau. But I won't say anything more about that. The main tool we need here is Schoenstedt's theorem for matchings. For permutations, it told us when we applied this Rsk algorithm how to read off the length of the longest increasing and decreasing subsequences. And a completely analogous theorem is true for matchings. Here we have our matching M. We look at the oscillating tableau phi of M that we get. The crossing number of M will be, well, this is just saying the length of the longest column of any of these shapes. We don't know where this longest column will appear, since we're adding and removing squares at every step. But wherever it does appear, that will be the crossing number, and the nesting number will be the length of the longest row among all these shapes. And the idea of the proof is, which I won't say anything about really, except that we can reduce it to the ordinary Rsk algorithm. And then you apply the ordinary Schoenstedt's theorem. So, for instance, let's go back to this example here. The length of the longest column is 2. So that is the crossing number. And indeed, 2 is the most number of edges that pairwise cross. And similarly, the length of the longest row is 2. So that's going to be the nesting number. And indeed, there are these 2 nesting edges and no more. Well, now, given this theorem of Schoenstedt, it's easy to see why the crossing and nesting number are have a symmetric joint distribution. Suppose M has crossing number I and nesting number J. Apply this oscillating tableau algorithm here. And now we can define a new matching to be the one that corresponds to the oscillating tableau we get by conjugating every shape. It's still an oscillating tableau, obviously. If we transpose every shape, we still are just adding and removing a square each step. By the uniqueness by the fact that phi is a bijection, there will be this unique M prime such that phi of M prime will be this oscillating tableau. Well, clearly, if we transpose each shape, we have changed the length of the longest column and length of the longest row. So, by Shensted's theorem, the crossing number of M prime will be J. That'll be the new length of the longest column here, and the nesting number will be I. So this map, M to M prime, is an involution on matchings, interchanging the crossing and nesting numbers. But it's quite a complicated involution. I don't know a simple way to see what it is without going through this oscillating tableau bijection. It would be interesting to find a more direct bijection. And so as I said, we have now proved this theorem that these two distributions, these two statistics have a symmetric joint distribution. And, as I said, it's open to find an analog of this simple permutation reversal interchanging I, S, and DS. What is an analogous bijection that interchanges the nesting and crossing numbers? Okay, so now we can start thinking about the question of enumerating matchings with a given nesting or crossing number. This is the analog of what Gessel did for this UK of n, giving this determinant of Bessel functions. Once we have such an enumeration, we can try to figure out the asymptotic behavior as n goes to infinity. So, let's say that M is our matching with crossing number at most k. That means that in this associated oscillating tableau, the longest column length is at most k. So these permutations are all just k-tuples of non-negative integers. So we regard each of these partitions in this oscillating tableau as a k-tuple of non-negative integers. And so the oscillating tableau is just a certain walk on n to the k-tuples of non-negative integers. The number of matchings on 1 up to 2n with crossing number at most k is the number of lattice paths of length 2n from the origin to the origin. That corresponds to starting out with the empty shape and ending up with the empty shape. In this fundamental region of the symmetric group, but in this region where the coordinates are weakly increasing, because we always have the shape of a partition, and if we read the parts in reverse order, there will be weakly increasing, and each step is plus or minus a unit vector, because in this oscillating tableau, at each step we add or subtract one square. Now this set of integer points, well, if we replace n to the k with a non-negative real numbers, we can think of it as sort of tensoring with non-negative real numbers to make this over the non-negative reals, is just the fundamental chamber for the Weil group of type BK, the hyperoctahedral group. So we're doing a certain kind of random walk on a fundamental chamber of a Weil group. Now these have been studied quite a bit, and in particular, Grabner and Magyar applied this Gessel-Zeilberger reflection principle, which is this very nice generalization of this famous André reflection principle, to solve this lattice path problem, to count these lattice paths in this fundamental chamber. And this is what their result turns out to be. Again, it's a determinant involving Bessel functions, but it's a determinant of a difference between two Bessel functions. These are the same Bessel functions that appeared before in Gessel's result. If fk of n now, this was the number of matchings on two endpoints whose crossing number is at most k. We look at this generating function. Now it's just x to the 2n over 2n factorial. There's no square here. It's given by this determinant, k by k determinant of difference of Bessel functions. On k equals 1, well, we're going to get a 1 by 1 determinant, this difference, and indeed we get the Catalan number generating function agreeing with the result I stated before. And as I say, this should be compared with Gessel's result for longest increasing subsequences, where we got this single determinant. Well, given this determinant, we can try to do the same kind of asymptotics that Bake, Deift, and Johansen did with this one. And indeed, this was done by Bake and Rainsel. They didn't state it in terms of crossing numbers of matchings, but they did look at the determinant in another context. And we end up with this result, the analog of the Bake, Deift, Johansen result. The limiting distribution of the crossing number of a matching on two endpoints. The mean now turns out to be the square root of 2n. Again, the standard deviation is order n to the 1/6, and we can state it this way. The probability that CRN over minus the square root of 2n divided by 2n to the 1/6 is less or equal to t over 2 is this sort of modified Tracy-Widom distribution f1 of t, defined in this way. Square root of the usual distribution and a little extra factor involving Pan-Lavey. I've restated Tracy-Widom distribution here and Pan-Lavey equation here. Okay. Well, the last thing I could mention is that one aspect of these matchings that doesn't exist in permutations is that we can try to count matchings of 1 up to 2n with a bound on both the crossing and nesting number. For permutations, this would be counting them with a bound on the length of the longest increasing subsequence and the length of the longest decreasing subsequence. That would not be interesting because that's 0 for n sufficiently large by the Erdos-Zakoris theorem. Well, this is really boils down to a walk inside of a finite region. It's a walk on a finite graph. And so it can be done by solve, in principle at least, by well-known linear algebra methods. This is the graph. The graph of all standard Young tableau that fit in all partition shapes that fit in a rectangle, an edge between two shapes that differ by a single square. And we want to count walks from the empty set to the empty set of length n. You can see we're just counting oscillating tableau, but they're constrained to lie inside this rectangle because we have a bound on both the crossing number and nesting number. And as I say, standard methods will give us this a determinant like this. It's a rational function whose denominator is essentially the characteristic polynomial of the adjacency matrix of the graph. And what's interesting about this, I guess my time is quickly coming to an end, but Grabner implicitly found the eigenvalues of this matrix A. They are these trigonometric sums. And so that allows us to deduce in particular that since they lie in a certain algebraic extension of the rationals of a given degree, to conclude that this denominator is going to factor a lot. All of its factors have degree dividing this small factor. Here are some examples. Like for j and k equals 3, the denominator will factor like this. An interesting open problem is it's not yet known when the adjacency matrix of this graph for which rectangles is this matrix invertible. Even though we know the eigenvalues of the matrix, and we also have a formula for the multiplicity of each eigenvalue, you think from that it's trivial whether it's invertible, but these multiplicities are also trigonometric sums, and it's not so clear when they're zero. So maybe there's a simpler way of attacking this problem. So I will stop here. Thank you.